Record on this. Okay. And the second speaker will be Derek Ward-Thompson, who will be speaking about the Event Horizon Telescope, which I personally am particularly looking forward to because I used some pictures of their disk drives being offloaded with a forklift truck in one of my talks. So without further ado, the running order will be speakers will speak for about 30 minutes and then take questions. I won't be that strict with time, but I will try and make sure that we're not here all night. The next talk is a little bit out of sequence. It will be at the end of the month, and please keep your eyes open for the email coming round with a link on that. If anyone doesn't get the link, please contact Paul or I directly or via the BAA website, britastro.org. So without further ado, can I ask Michiel Klaassen to take the mic and share his screen?
Yeah. Okay. Welcome, everybody. Because it is getting very dark outside, I first go outside and let you show some shadows of the telescope, because else it is too dark. So I want to flip the camera, but I don't know how to do that. I'll try. Oh, oh, yes. Okay, yeah. Okay, well, we go outside. I take my torch with me. Oh, well, it is reasonable light for the camera. And I have a torch here, but this is not necessary. I'm walking now outside. And here you see the dish. It's a Gregorian optics. It is a hollow second reflector, and the horn is in the center. And at the end of the horn, the radio LNB is placed. It is a normal LNB, but I modified it because the temperature drift of the crystal was too much. So now it is coupled to a GPS disciplined oscillator. Leo Bodnar, I think you know the name. That is very, very famous. I have two units, one for frequencies and other for other things like signal generators. If you look now to this part, you see it is very dark. You see the counterweight, and it's very important because in the beginning I had a 3 kilowatt elevation motor, but it required so much power that the power dips were crazy. So that was could not be held like that. So I added counterweights, and now I can move the dish with a 1 kilowatt motor. It is a warm worm pole. You can see perhaps the black slanted tube, and if you look very carefully, then you see a wheel. For emergencies, you can rotate that wheel and then lift the dish up or down. I'm not going upstairs now because it will be dark and it is difficult to see. And when you bump your head, the steel always wins. So that is not nice to meet solid steel. Then I go down. Here's the ladder. Then I go down, and then we have here the base, the concrete base, 20 tons of concrete. The telescope itself is about 8 tons. I've made the wheels also by myself. This is steel wheel. There are 4 wheels on the corner of each corner of the rotating frame. The rail itself is completely loose. It is not fixed to the concrete. It is only held by clamps so that it won't shift. That is done because of the expansion of the rail when it gets hot. This is the instrument for the wild pigs here, but it works. But the pigs don't give anything, give a damn about that instrument. So it's a waste of money. Here you see the GPS antenna, which is coupled, and we use that, what I said, for frequency generation. Down again, then you see here the limit switch. There's a limit switch for the azimuth direction, and here you see the drive wheel of the telescope. It is a forklift truck wheel with also a war wheel to rotate it. It is mounted on a hinge, on a plate. It is mounted, connected with hinges to the frame of the container so that it can move up and down. It is set under tension with a leaf spring so that the wheel is pushed with about 150 kilos onto the concrete wall. Here you see the limit switch 3 points, one for the 2-degree direction and one for the 258 degree. This is meant to give way when the pressure is too much because of the heat. It can be 40 degrees here. Sometimes in the summer it is very, very hot. So that will give way, and with rubber it pushes back again, so that the rail would not bend. Okay. Of course we have of course we have also clamps. Very, very important. These clamps will be connected to the base when it is in a parking position. There are 4 clamps, and there are extra 2 chains just needed when there is a storm or so, or high wind. This is one point to fix the clamp, and here in the middle you see another one. Here you see some advertisement in a modern way with a QR code. Oh, it is still possible to film with so less light. This is the back side of the dish, a huge bus or hub where you can step into and do all kinds of things. Camera on the corner for the bad guys. There's an indicator to see if the software is correcting the dish azimuth of the dish into the parking position. Here you see another clamp which is down. Okay, now we go in again. Oh well, let's start here. Several PCs. The right one is used for instruments to connect to the instruments like Rode and Schwarz, and to the Bodnar, Leo Bodnar generator, GPS generator. This connected to an amplifier, and then a cable, a coax cable goes up into the secondary mirror, and it gives a reference frequency for the receiver. The second PC is not on. It's just a computer to make fast calculations, intended for next year perhaps, for fast radio bursts, etc. And then a normal PC for internet, but also for controlling the frequency of the crystal, or actually the replacement of the crystal. 27 megahertz is set to, and it's going to the second Leo Bodnar unit, and this is also connected to that GPS receiver or antenna. Well, it is a bit erratic, all, but okay. This is a small PC laptop which is used to measure the muons. The muons. This is a small printed circuit board which you can buy on the internet, and there are 4 cables, or 2 cables and 4 connectors, and then connected to those boxes in the corner, one over there and one over there, so that you get the direction of the muons. If both the sensors are stricken or activated, then the muon is counted as valid. I can take it off. There you see a printed circuit board with a high voltage generator, and some other chips to make the pulse to lengthen the pulse. You see here the 2 Geiger-Müller disc-like sensors, and with these sensors, with one here and one over there, you can get a direction straight up, but with this one, oh, to the right one, you get another direction. So that is what I intended to do. Under the ventilator, you perhaps I can show you in short the motor. Oh. It's very small motor, 0.7 kilowatt. What I said, you see the hinges and the leaf, the spring leaf. Are you still there?
We certainly are.
Yeah. Oh yeah, I see familiar face. Okay. Okay, now I wanted to show you how to make a measurement with the telescope, a real live measurement. Can you see everything? Yes, I think so. Because this is the control panel of the dish. I wrote everything. Mostly I wrote everything myself, mostly in Python. It is almost on target, so there's not much to adjust. Just as a test, I activate now the Leo Bodnar generator and see if the peak, yes, there is a signal coming on the right spot, on the sharp, on the sharp program. Okay, so that's okay. Now I will stop this program and process. He wants to be sure. And then what I already filled in is this program, cflat.exe. I wrote that also myself. It is a program which adds spectra together, 100,000 spectra added together in 5 minutes. And that's a lot, because the signals are very weak. You cannot use what radio amateurs do often, just average your signal, because that is not sufficient. You have to add it all together and then divided by the number of measurements you take. So now we are measuring the dark or the reference of the sky just beside the signal. This is I'm aiming to W3OH. Okay, now we have a signal here, and that is the version in 1 minute, because we don't have so much time. And now I start the dish, and you hear the squeaking of the V-belt. And the elevation You can see perhaps the elevation. The azimuth is already on spot, but the elevation has to adjust about 5 degrees. This is 5 degrees. This is the actual elevation, and here this is the calculated setting. So you have about 4 degrees still to go. And meanwhile, this program is gathering its data. This is the reference. This is the in between data. And when the dish is on its designated spot, then we have to measure another 1 minute. And then we should have some data. Yes, it's on the spot. Okay. Now it's tracking. You see the tracking is about 0.002 degrees error. The thing is, in the beginning, I had a lot of trouble with the elevation because of the concrete wall. When the dish is rotating onto the concrete wall, the wall is not flat. It is a bit wavy. I asked to make it flat, but the contractor could not do that. So later on, in the beginning, I had a correction table, but it was horrible. And now I have an absolute elevation detector. I cannot show it because it is now dark and it is up in the hub. Okay, well, let us try if we have some results. As always, four. No, not yet. A little bit of elevation you see here. Perhaps we have to wait some more time, but this is the beginning of the signal of W3OH. Normally, I take the 5-minute integration time, but because that takes too long, it is 5 minutes for reference and 5 minutes for measurement. It's 10 minutes, and in that time you have to wait, and that is not for everybody, given for everybody to do. It is getting better, but it is not so good, and that's of course it is still a bit low. The elevation is a bit low yet. It is now 26 degrees in elevation. Let me see. Six. Well, it is it is rising a bit, but it is not spectacular. So perhaps I can show you something else also. Um, mhm. Yeah. Okay. Normally you see something like this. Can you see it? I hope so. And these are, I think, these are 5 minutes integrations. So that is that looks a lot better. Yeah. This is clearly the demonstration effect. I will find the where is it? We have a look at the website. Oh, the website. Normally it is something. Oh, it's something like this. All bumpy here and flat again. These are all clouds rotating in a region and trying. You see here all these results, which are added together to get something like this. These are all clouds rotating around each other, and mostly the sun is not formed yet. It's just a rotating bunch of clouds. And that's the funny thing with the optical astronomy. You can't see that. You can only see that with radio astronomy, with radio signals. When eventually the star ignites, then all these extra clouds and are blown away, and the star is shining brightly, and only the solid rocks like planets will stay. But the rest of the clouds, which we could see in the beginning, are gone, and so the radio astronomers are blinded because they don't see anything anymore. All the clouds which are measuring just the same principles as a laser, but then for microwaves, are gone. And then you get the long road of the star to mature, and eventually it will burn up all its energy by combining hydrogen molecules into heavy elements. And when all the elements are when there is no hydrogen left, then the star will die. Sometimes with a loud bang, but mostly it will be enshrouded in all the clouds it's making, and then we, as radio astronomers, we can see it again. I will show what I mean. Perhaps you see it like this. Oh, these are, well, I put on, switch off the light. Perhaps you see all these dots. These are rotating around something which is not there yet, but will form a star in the center. An example is, for instance, W3, but also Cepheus A. It is a very nice example. And what I said, when there is a formation of a star and it is dying later on, then you get something like this. All the rings you see are material like oxygen, silicon, carbon. All these things are being made by the star, but the star is not visible anymore. But we can the outer and colder layers are cloudy again, but very cold, and then it is amazing again, and we can see them again. So in the beginning, we can see a baby star, you can say, and at the end we can see a dying star. It's a bit sad, but that's the way it is. And what is interesting, of course, that these stars are making the elements we are made of. So in our solar system, we have also heavier elements, but it is not made by our own sun. It is coming from other dying stars.
Okay, Michiel, I'm going to say, could you wind up, and are you willing to take some questions?
Okay. That is good that I didn't do more, because it is a very short time, yes.
We'll invite you back.
Okay.
I've got a couple of questions in the chat, which one is somebody admiring your bravery for doing a live online demonstration and measurement, which absolutely true, the curse of live television. And the second question is this, are you observing at 1665 megahertz?
No, at 10 gigahertz. 10 gigahertz.
Right. That
That
answers that.
That is the amazing frequency of methanol. I can show you the frequency in my sheet. Oh, it's actually amazing frequency is 12 gigahertz, and it's the LMB local oscillator is 10 gigahertz. So we tuned to 1.5 gigahertz. I skipped the complete calculation of the velocities of the star, of the region, I have to say, and our own velocity, because we can. This is the Mason frequency, but when you tune to that frequency, you see nothing. Why? Because the cloud which is emitting this frequency is moving with minus 45 kilometers per second. That's not the only thing, but we also in our solar system rotate around the sun with at this moment in that direction of the star with minus 20 kilometers per second. So you have to add those two together, then you get a sort of kind of correction velocity, and then you can calculate with Doppler that the receiving frequency is different from the original frequency. So the original frequency was, Mason frequency was 12.178, but the sky frequency, where we have to what is coming here into our atmosphere, is 12.18 megahertz of gigahertz. 12 gigahertz is 1/8. It's about 3 megahertz difference. So if you look at this frequency at this, and with a small bandwidth, you cannot see it, but you have to tune it to the correct sky frequency.
Okay, I don't have any more questions in the chat. If anyone would like to ask one, yes.
A bit of background. What I've known Michael for some time. What he didn't say was that his antenna is about 9.5 meters across. It started off in life in Holland as I think an ex-military satellite tracking antenna or something like that. Yes. And he managed to acquire it, and single-handedly he took it apart, put it in a container, and shipped it to its present location in Portugal, and assembled it all together. Everything you see there is his own work, and maybe you ought to get him back sometime to tell us in detail how he did it.
Yeah.
Thank you, Michael.
Yeah. Thank you for your extra information. Yes, indeed. I skipped that all because it is too much and it takes too long. So, but there are nice stories to be told also about that. It was midwinter, minus 10 degrees. I took, I think, 3.5 weeks on my own to take the telescope, or the satellite dish down and deassemble it. The biggest problem was one of the problem was to get these very heavy beams and the hub into the container because I couldn't push it. It is impossible because it is so heavy. So what I did is, well, perhaps I can show you. Oh, it is too dark now. Oh no, it is not this. Oh. No. Where is it? Oh, here it is. Yeah, here. I drilled a hole into the wall of the container. I put the rope through. I put one end to the very, very heavy beam and the other end to my car, and I pulled everything into the container like that. So that was a relief because I didn't know how to do it else because there was no one who could help me. You know,
okay.
I put some things around it to get onto up there. But yeah, that was interesting.
Michael, we
also
have another question.
Yeah,
Just interrupt
okay.
you. Jose, can you unmute yourself and ask your question, please?
Yes, sir. Good evening, everybody, and good evening to Michiel. He contacted me 12 years ago when he pretended to take the dish to Portugal. I'm CT4AN, Michiel. I'm ready to. And I would like to ask you, how do you, I think you calibrate all the levels you use, and I would like to know with so big dish and with those systems, how do you calibrate the levels for the system to make calibrated results?
Well, I just that is very difficult to do because it is not one receiver I have, but I have several receivers for all these different frequencies. So for every one I should calibrate that again and again. So I didn't do that. I just took a well-known source and then compare that to other sources I measured. So that is how I did it. Because it takes time, but also it takes a lot of instruments which are very expensive. So that is why I didn't do that at this moment. But this is one of the things I will do in the future.
Okay. From my side, my congratulations for all the work done during all these years. And I hope you have a new street for the radio telescope quickly. And eventually, I'll make you in the future.
Yeah, I have a bit of trouble with the communication. I touched something which I shouldn't. Oh no.
Okay. Can you still hear us?
Yes, I still, but it is very small. Oh, yeah. Oh yeah. Now it's back again. Sorry.
Okay. Just to say that
I will try to reverse the camera again. Yes. Yeah. Well, here
okay.
I am. Okay.
Just to say that Ted Klein has posted some links for videos and the website for Parac on the chat. Are there any more questions, Michael? No. Well, Michael, thank you very much for a very interesting and entertaining introduction to your telescope.
Yeah.
We will ask you back if you're willing to come.
Perhaps next year we can do some more.
Yeah. And now to add to my questions about, I asked Whit Reeve, who I believe is on on the call tonight about polar bears. We've now had pigs affecting radio astronomy. And that's, I think, something to add to the list of hazards of astronomy. So now, can I ask Derek to unmute himself and take the floor for the next presentation?
Thank you, Andrew. Hopefully you can hear me. I've got you all on gallery at the moment, so if you wouldn't mind switching your cameras on, if you can, or if you don't object to, so I can just say hi to everyone. It's a very great honour to be invited to talk to the BAA. I was a member of the BAA myself a while ago. I joined, I think, at the age of 13 in about 1975, and I think I was still a member till about 1990, by which point I'd been a fellow of the RAS for a number of years, and I left the BAA at that point. So it's a great honour to be among fellow BAAists, but also the radio astronomy section, to talk to a group of fellow radio astronomers. Now I know you're not all technical involved in the technical side, and perhaps some of you involved in the technical side, but not the astronomy interpretation. I gather we've got a very mixed audience, but we all have one thing in common, which is that we love our radio astronomy. So hopefully I'll be able to impart some of the excitement that I've felt in the work that I've been really fortunate enough to be involved in the last few years. So, without further ado, let me see if I can actually successfully share my screen. There it is. Share. So, I'm going to switch my video off because I find it quite off-putting seeing myself so close to the camera, and going to start the slideshow, hopefully. So hopefully you can now see my first slide.
Yes, that's worked fine, Derek.
Jolly good, thank you. So you're all probably reasonably familiar with these two pictures, and what I'm going to talk to you about is how we took the pictures and what we learned from them. So in April 2019, already 5.5 years ago, it does not seem like that to me, the first papers appeared of the black hole, the first ever picture of a black hole that had been taken, and this was the M87 star black hole. And six papers, we published 6 papers simultaneously, and a further 2 around the polarization came out a couple of years later. I should say my contribution to the collaboration was on the side of polarization. So we'll talk a little bit about that and about the magnetic fields a little bit later on. And then Sagittarius A star came along about 3 years later. And once again, it was six papers. And earlier this year, I haven't added it to this slide, but earlier this year, the two polarization papers also came out for Sagittarius A star. At the time of the M87 star release, it went absolutely viral. You'll probably all remember you couldn't turn on a television or a radio without hearing about it. You couldn't open a newspaper without reading about it, and it even made the front pages of the Times and the Guardian and pretty much everything else. Now, interestingly, to us astronomers, Sagittarius A star is more interesting because it's our black hole. It's the black hole at the center of our galaxy. For some reason that I don't understand, the rest of the world didn't agree with me on that one. They didn't find it quite so absorbing as the first one. And I can tell you that, however, I can tell you that it made the Lancashire Post and the Blackpool Gazette in terms of its broad reach, and you might have seen it in a local newspaper near to you. Our own publicity guru, when I was telling him about it, obviously I was allowed to break the embargo to get our own publicity team up to speed. And his comment was, "Is it another fuzzy donut?" And yep, well, I'm sorry, yes, it is just another fuzzy donut. But I guess for the rest of the world, it's like once you've seen one black hole, you've seen them all. And didn't really share our excitement in this. But nevertheless, I'll try to impart some of the excitement to you as we go along. So how was it done? Well, we took a bunch of radio telescopes from around the world and linked them together. Now, that's a very easy statement to make, but in terms of how to do that, it is really quite an impressive feat. Now, I say I wasn't part of the team, the technical team that actually did this, and I have nothing but admiration for these folk because I'll try and give you some flavour of the technical challenge involved in this and how just absolutely everything was sort of difficult squared. And it's just, there's a reason why it hadn't been done before, let's put it that way. So you've got a bunch of telescopes. There's a telescope in Greenland, various telescopes, Mexico, South America, the US, Hawaii. I'll talk about the Hawaii telescope in a minute, and Southern Europe, Spain, Southern France, and so on. The telescope that we have a sort of link to is the James Clerk Maxwell telescope in Hawaii. And I was fortunate enough to pay my first visit there in October 1987, only narrowly missing the official opening by Prince Philip earlier that same year. So I didn't get to meet him, I hasten to add. It's on top of 14,000 foot extinct volcano, and it is a high frequency, essentially microwave radio telescope. The Gore-Tex screen that you can see covering the dish is to protect it from the wind-blown volcanic dust on the ground there, and also from the wind itself, which can cause the telescope to oscillate making the pointing exceedingly difficult. But if you climb up enough stairs, which I did to take the right-hand photograph, and stay under the Gore-Tex screen, you can look down on the dish, as you can see it there. The doors are shut at this point. This is during the day. And just the ordinary lighting is on. That dish is 15 meters in diameter, which to you and I is about 50 feet in old money. And the surface accuracy of the dish is about 25 microns,
Wow.
25 micrometers, or 25 thousandths of a millimeter across the whole of the surface, which is really quite impressive. But if you want to get to the really high frequencies that we're working at, then you need that kind of level of accuracy. And the frequencies that we're chasing are in the hundreds of hundreds of gigahertz regime, chasing up towards a terahertz. So you're talking millimeters and sub-millimeters, for those of you who think in wavelengths. And my university, University of Central Lancashire, is actually a part owner of that telescope, and we've had a share and an interest in that telescope since it opened. So this is why we in Preston have access to the whole Event Horizon telescope. So, just a quick recap. Why do we need ever bigger telescopes? Well, there's two reasons. One is to collect more light. The bigger your dish, the more photons you catch. Just like the bigger the bucket you put out in the back garden in the rain, the more rain you catch. And also, the other aspect is the resolution. And I'll talk about resolution a little bit. Forgive me, those of you who are already familiar with it. For the general public, I call it zoom, but of course, you know it's not quite the same thing. And of course, the other reason that there is a third reason why astronomers like bigger telescopes is just to be like bigger toys, and the bigger the toys, the better. But what if you only need the resolution and the object you're looking at is bright enough that you don't need to collect as much light? So the analogy I use is here is a picture of an optical telescope, and I say, imagine throwing a tarpaulin over the whole of the telescope mirror. The optical astronomers would probably murder us for doing that. But then you cut two small apertures, holes in this tarpaulin, one at each side of the mirror. And then you took a picture both with and without the tarpaulin. Obviously, the picture with the tarpaulin over would be much, much fainter, but it would have the same resolution. And that's the interesting thing. And that is the that is the trick that radio astronomers play. So, one quick recap slide on resolution. Remember, resolution is the smallest angle at which you can see that two objects are not one. And excuse me, I'm going to have a drink of water. The analogy I use for when I give popular talks is, imagine you're on a long straight road at night in the dark, and in the far distance you can see there's a car coming towards you. And to start with, you just see it as a single point of light. And gradually, as it gets closer and closer, you reach a point where you can actually see that it has two headlights. And it's the two headlights that you can see that had appeared just as a single point. At the point at which you can see it has two headlights, that is what we call the resolution. That the two headlights, you've actually managed to separate them. Now, I've followed Stephen Hawking's advice here, because Stephen Hawking, for those of you who've read his Brief History of Time, says in his preface he has kept in the entire book to just one equation. So in this entire talk, I'm just going to give you one equation. And it's not a terribly complicated one. It's this one down here, which says alpha equals lambda over d, roughly. Now, alpha is the angle at which this angle here, at which you can resolve that something is two objects and not just one. And so obviously we want that to be as small as possible. We want to resolve the two headlights of the oncoming car as far away as possible. And that goes as the ratio of the wavelength you're observing at divided by the diameter of your telescope, d. And the diameter of our telescope, if you remember, once we've thrown our tarpaulin over it, is the distance between the two apertures in the tarpaulin. And what's the largest we can make d with our radio telescope? Well, we can make it potentially the size of the Earth. And that's what the Event Horizon Telescope has done. Now, there's a sort of illustration here of what resolution is doing. In the left-hand image, you've got two telescopes, one in, I believe, Arizona and the other in Mexico. And that is the size then of our telescope, the distance between them. And you just see the single headlight of the distant car coming towards you. Now, what if you had another telescope in South America, in Chile? Suddenly you've got quite a long baseline north to south. And so suddenly north-south, you've got some sort of resolution, and suddenly 2 points appear. At last we've got the two different headlights, but that's going from Arizona to Chile. Now let's add in Hawaii, and suddenly we've got some east-west resolution as well. So suddenly east-west, we can see two things, as well as north to south. Finally, we add in Spain and Europe, and we've got east-west and north-south, and suddenly we see the image, or we start to see the image. And you can do the calculation. If d is of the order of 10,000 kilometers-ish, which is the order of the diameter of the Earth, and if we can get lambda down to a millimeter, that's what we're trying to do, then alpha, our resolution, is 20 micro arc seconds. Now, you all know that typically on a clear night that's cold and crisp and dark from this country, with an optical telescope, the atmosphere allows you to get to about 5 arc seconds. Maybe if you're in a very good sight, you'll get to 3. And remember, an arc, 1 second of arc is 1/3600th of 1 degree. So imagine being able to get down to micro arc seconds. A micro arc seconds is 1 millionth of a second of arc. So just to put that into perspective, if you had an optical telescope that had that resolution, you'd be able to see an object the size of a tennis ball on the surface of the moon. I mean, it just, the numbers I find personally just absolutely staggering. But this is what you need to do if you're going to make progress in this subject area. And so here's a representation of all of the different telescopes. The ones in red are actually telescopes that have closed, but that the group are hoping to be able to reopen. The ones in yellow are the ones that are being used, and the two in green are the ones that are hoping to bring online very shortly. So obviously, you can see sort of Greenland to the South Pole. You can't do much better than that in a north-south array. Of course, you've already twigged. The problem is that the two of them can only simultaneously see objects close to the equator. So you're limiting your number of things that you can observe with Greenland and the South Pole simultaneously. There is another telescope on Hawaii, the sub-millimeter array, and together with the JCMT, that gives you a tremendous east-west baseline, basically from Hawaii to Europe. Now, putting radio telescopes together is not a new idea. At Jodrell Bank, you've got the big Lovell dish, but you may be aware that it is in fact part of a radio network across the UK, well, across England, that's known as Merlin, the multi-element radio linked interferometer, or whatever it stands for. And then across Europe, we have our own network of dishes. The Americans have something similar, and you're probably aware that they link together, talk to each other, and have made many successful observations over many years. But this was all done, remember, at centimeter wavelengths. So that's not to belittle the effort here. That's a huge amount of work. But what if we could go to millimeter wavelengths? So we've made D as big as we possibly could. D is the size of the Earth. Let's make lambda smaller. The bigger D is, the smaller is alpha. The smaller lambda is, the smaller is alpha. So this ratio, if we can get the biggest D we can and the smallest lambda, that's going to give us our best resolution. And that's the incentive from going to centimeter radio, from centimeter radio to millimeter radio. But that presents its own challenges. So, quick reminder for you on radio interferometry. If you're looking at a source that's marked in the direction of this vector S, then you've got light traveling from this source, parallel light rays coming to your telescopes. The solid lines are supposed to be ray diagrams. The dashed line is one particular wavefront of that ray, which reaches one telescope before it reaches one of the other ones on a different continent. And so that is known as a time delay, and that delay is here signified by tau, which is a function of d, the distance, and also the angle your source is above the horizon. So tau is not only quite small, it's also constantly changing. So you have to measure the time of your incoming signal incredibly accurately, because typically the travel time between one continent and another will be microseconds, if not smaller. And so you have an atomic clock at every telescope, and that atomic clock timestamps the data. So you can keep the data, you can put the correct timestamp together with the correct data from another telescope. But the other thing is, as you're probably all aware, if you're using any optical system, where it's a optical telescope, radio telescope, whatever it is, your optics have to be better than the wavelength that you're trying to observe. In fact, typically, you would say it has to be 10 times better. Lambda over 10 is kind of the order of magnitude. Oh, excuse me, I thought I was going to sneeze. The the accuracy that you need. So when astronomers were working at centimeter wavelengths, then they needed accuracy to about a millimeter. Now that we've gone to millimeter wavelengths, we need accuracy to about 1/10 of a millimeter or better. And 1/10 of a millimeter is only 100 micrometers. On those scales, when you're looking from one continent to another, you have to take into account tectonic movement. The movement of the tectonic plates of the Earth starts to become important. I mean, we're using atomic clocks and we're worrying about tectonic shift in order to measure all of this. And of course, we do it using laser ranging to satellites and such like. But you literally need the accuracy of lasers to do it. So it's not easy. Hopefully I've got the gist of that across. One other little thing we need to mention is what it is we're looking at and why. And in order to understand gravity, and certainly in order to understand black holes, we need to understand relativity. Even if only at a what I would call here a pictorial level. Now, Newton had this idea that gravity was a force. The sun pulls one way, the planets pull the other. They have this giant cosmic tug of war. Einstein said, no, that's wrong. Gravity isn't a force. Gravity is just a manifestation of the curvature of space. And when you put a large, massive object, such as a planet, into space, you curve space. So here, for instance, you put the sun in space and you curve space. What this means is that, and this is the testable difference between Newton and Einstein, is light appears to curve. Now, the commonest misconception I come across when seeing people trying to explain to members of the public about general relativity, they say, oh, gravity curves light. And it doesn't. Light goes in a straight line. Gravity curves space, which means that in curved space, a straight line is curved. And by a straight line, I mean the shortest distance between 2 points. And we're just used to that being a straight line because we're used to drawing on a piece of paper or whatever. But once you get into curved space, then the shortest distance between 2 points isn't a straight line necessarily anymore. And light follows what we call a geodesic. Now, geodesic, for those who aren't familiar, is simply the shortest distance between 2 points in a curved geometry. What the heck does that mean? Right, well, the analogy I use is if you've ever flown in an aeroplane across the Atlantic, and you get on it in Britain and you fly across the Atlantic, that plane will follow what's called a great circle on the surface of the Earth. The Earth is a sphere, and the shortest distance between 2 points on the surface of a sphere is called a great circle. Now, if you looked at your old school atlas and the Mercator projection of the Earth, and you looked at the path that your aeroplane was taking, perhaps you take off at Heathrow, it goes an awful long way north over Greenland or whatever, and then comes back south again over Canada and then down into the US. Say you're flying into Los Angeles, it comes down over the west coast. And you're looking at your Mercator projection, saying, where on earth is that pilot going? But you look at the same thing if you've got a globe of the Earth, and if you look at it from the correct angle, you can actually see this straight line, this great circle. So we're all familiar with the concept of a geodesic, and that's what light does. So as far as light's concerned, it's not curving. It's just minding its own business, going in a straight line. And so at the time of an eclipse, you can, with the right equipment, see a star that should actually be behind the sun, because the curvature of space has curved the geodesic path that light is following to get to your telescope. Space, incidentally, has 10 to the 20 times the tensile strength of steel. That's a 1 with 20 zeros after it. It takes a lot of mass to curve space, or to curve it to any measurable amount. In the case of a black hole, and I'll come back to this in a minute, this is the extreme case where space has curved so much, you've broken it. And another way of looking at this is, you're all familiar with the concept of escape velocity. A rocket has to be traveling away from the Earth at 11 kilometers per second before it can escape the gravitational attraction of the Earth. On the moon, that's 2 kilometers per second. On the sun, it's about 600. And of course, the hypothesis is whoops. My screen has gone blank. Can anyone still hear me?
Yes,
still
we
hear
can
you
still
and
hear
see
you.
you.
For some reason, my laptop has suddenly gone blank. What's happened? Let's put it back. Can you still see my slide?
Yes,
Yep.
yes.
Oh, that's okay. Sorry, I don't know what's happened there to my laptop.
Yeah, Dirk, could I just say, could you sort of think about concluding in about five minutes or so?
Perfect.
Sorry.
That's about what I've got left.
Fantastic.
What if the escape velocity from an object was more than 300,000 kilometers per second, which is approximately the speed of light? What we also know from relativity is nothing travels faster than the speed of light. So even light itself wouldn't escape. And hence we had the concept of a black hole. I'll skip over how black holes are formed and go straight on to where we see them. So this is meant to be, this is a kind of schematic of, this is meant to be the Milky Way galaxy here, and we've got M87 up here. So why didn't we look at our own, and the blue star is meant to be us. Why didn't we look at our own black hole first? Well, because we have to look through a lot of gunk in our own galaxy, whereas the black hole in the center of M87 star, we can see face on without looking through the gunk. And the other thing we can look for, how do we know where to look? I mean, by definition, it's black, is that black holes are predicted to have these things coming out of them that we call relativistic jets. And the idea is that matter spirals in to the black hole through what we call an accretion disk. It accretes onto the black hole, and some fraction of the matter is ejected along the poles. And that should be to us a signal of where a black hole is. And M87 star has one of the clearest, M87 has one of the clearest jets that you can see, and you can see it at almost every wavelength. So that was the reason for looking at M87 star. And lo and behold, you look at M87 and you find a black hole. And that's what it looks like. Not surprisingly, it's black in the middle, and this area around it, you are seeing this accretion disk of material spiraling onto the black hole. So people were can model it. Don't worry too much. GRMHD stands for General Relativistic Magneto-Hydrodynamic Modeling. So there's an awful lot of physics goes into that, and an awful lot of computing time. So here's the picture. Here's what the computer predicts. You blur it by the resolution of your telescope, and this is what you get. And the way people interpret the pictures is in this way. You make a physical model in a computer. You look at predict what it should look like, blur it to the resolution of your telescope, and compare it to what you see. And when you put all of the parameters in, you predict that the black hole has about 6 billion times the mass of the sun. But also one side's looking brighter. That's the other thing you notice. Why is that? Well, this is a thing called relativistic beaming, which is where if something is coming towards you at a significant fraction of the speed of light, here we've got 98%, then the light that it throws out is no longer in all directions, but it's beamed forwards, sometimes known as the lighthouse effect. So the idea is one side of the disk is coming towards us, the other side is going away from us because it's orbiting, and hence one side looks brighter than the other. And you can also measure the rotation of the jet from Doppler shifting, one side of the jet to the other, and you find everything is going in the same direction. You could make models where everything's going in different directions, but fortunately we've got the simplest case where everything's rotating in one direction. Now, just to give you the scale, okay, these two things look the same size, but they're at very, very different distances. M87 star is an absolute monster. Okay, the event horizon radius is greater than the radius of Pluto's orbit around the sun. It is absolutely bonkers at 6 billion times the mass of the sun. Sagittarius A star, the one in our galaxy, well, that's much more manageable. It's the entire accretion disk around the black hole would fit inside the orbit of Mercury. So it's much more manageable. Of course, what that means is that if you weren't sort of watching out of the window of your Starship Enterprise or whatever, you could actually cross the event horizon of M87 star without even realizing it. And that's a scary thought if you're ever planning on traveling anywhere in a spaceship. And finally, the bit that I was the tiny part that I was involved in, which is to measure the polarization. Now, I haven't gone into the physical mechanisms that we're observing in the radio, but there are, as you heard earlier, a number of different ways of emitting radio emission. What we're seeing and what we're measuring is what's known as synchrotron radiation. And if you can measure the polarization of your radio waves, you can infer the direction of the magnetic fields where they were emitted from. Because it's the magnetic field that causes the synchrotron radiation, and the synchrotron radiation is polarized. And these are pictures of the inferred direction of the magnetic field. And it's not circular, but it's not radial. It's kind of in between. It's kind of spiral. And we think this is how it arises, is that you have essentially a corkscrewing magnetic field coming up the poles, first up the North Pole and down the South Pole. And if you see that in 2D, the corkscrew looks like a spiral. And this is important because we think this is what creates the jet. So you've got a huge amount of matter spiraling in through this disk to the center. It's at very, very high velocity, 98% of the speed of light, say, very high degree of, very highly energetic, very highly charged plasma. And so it interacts rapidly and easily with the magnetic field. So the point of the corkscrew is some fraction of the material falling onto the black hole gets literally fired away, also virtually relativistic speeds, along the axis of the corkscrew. And that is the reason why you get a jet from a black hole. You think, well, a black hole, nothing can escape. Well, it can't, but this material hasn't had chance to cross the event horizon because it's got caught in this vortex of a magnetic field. So studying the magnetic field is very important to understand why black holes have these jets. And as I say, that's the work that I'm involved in. There's the Sagittarius A star picture taken in 2017, published in 2021. Final question for you. Oh, excuse me, I sneezed. Why doesn't our own galaxy have these jets? Okay, we've got this black hole. Okay, it's 1,800 times smaller than the one in M87 was 1,800 times closer. So you see it at the same sort of size. Why doesn't it have jets? Why aren't we living in an active galaxy? Why isn't the Milky Way an active galaxy? And this picture, which is a sort of combination picture slash cartoon, but with real data on it, gives us a clue. So here's the Milky Way, and in the purple, you got some results from gamma ray satellites. In the blue, you got results from an X-ray satellite. And what you see when you project it onto this sort of plane is you see that the Milky Way galaxy seems to have two what we call lobes, one above and one below, of energetic gas, hence the gamma ray and X-ray emission, but above and below the galactic plane. And we think this is evidence for how the Milky Way used to have one of these jets going like this, but for some reason the jet switched off, and it's just left these sort of bubbles that the jet has blown. And we think the reason why the jet has switched off is that at this particular moment in time, the area, the volume in the vicinity of our black hole is pretty empty. We look at the center of our galaxy and we see what we call the central cavity. Very, very, very low density material. There's essentially nothing there. So there's nothing to feed the beast. So there's no material to fall in on the disk, and hence nothing to be kicked out along the jets along the poles. And we think, but here we have evidence that there used to be. And at the moment, it's just used up all of its local fuel to eat. And so that's why we no longer live in an active galaxy. But if you go back a billion years or so, then our galaxy was active, which is why we've got a black hole, even though we don't have jets. The other last point to note about our black hole is because it's so much smaller, it is really much, much more dynamic, and it's changing all the time. So this picture in the middle is a sort of average picture. The four pictures along the bottom are the four different types of picture that were observed from the telescope, and the histogram here tells you how often we saw something like that. So this one was about the second most common picture that was recorded. This was the most common. This was the third most common, but slightly less so. But every now and then it looked like this, in this sort of small. And one of the things some of my colleagues are trying to do is to make a movie of the galactic center and see how the area around the black hole actually evolves with time. which, okay, what we've done isn't difficult enough, chaps. Let's try something even more difficult. But this is why it took 2 years longer to publish this picture than it did to publish the M87 one. It was because we couldn't actually decide on what it really looked like. You couldn't put together very long integrations. This is changing on timescales of anywhere from 20 minutes to an hour. So basically, the maximum integration time we could use was about 20 minutes. And then that's difficult because that doesn't allow you to go anywhere near as deep as if, say, you're observing and you were able to integrate your image for 8 hours. So in terms of, well, can we make movies? Watch this space. And I'll leave you with a sort of pictorial summary of my talk and say thank you very much for listening.
Derek, thank you very much indeed. Much appreciated. Are there any questions? Yes, there's one in the chat from Richard. Have magnetic fields and accretion disks with all this swirling hot material, is it possible for black holes to generate electrostatic fields as well?
Oh, yes. Yes, I'll put my camera back on. Yeah, yes, you don't get one without the other. So you've got incredibly energetic electric and magnetic fields, and you've probably got some gigantic and extremely impressive electric storms going on if you dared to get close enough to watch. And it would probably short out every electrical circuit in your spaceship. So you'd then drift helplessly into the black hole itself. But yeah, you can't get magnetism without electricity going with it. And these are some of the most, if not the most, active objects we know of in the universe electromagnetically. So yeah, the person who asked the question is absolutely right. They are really, really, really dramatic places, but dangerous as well.
Richard, I hope that answers your question clearly. Are there any more questions? Either pop them in the chat or just unmute yourself and ask.
Jose had his hand up a minute ago.
Okay. Jose, are you there? Do you have a question?
No, thank you very much. It was
Okay.
an operation mistake.
Right. I have a post in the chat. A famous quote is that black holes have no hair or only very few properties.
Oh, wonderful. The no hair theorem. We're in the process of being able to prove that theorem is incorrect. And that's because we are successfully measuring the magnetic field. Believe it or not, it's easier in the case of M87 star, even though it's further away, because it's bigger, and we've got the magnetic field spiraling inwards. Obviously, we can't tell what's happening inside of the event horizon, but not all of the magnetic field is heading out up along the jet. And so, by inference, some of it must be crossing the event horizon. And in the case of, as I said earlier, in the case of M87 star, the event horizon is not really a special point in space. you can cross it without knowing you've crossed it. You'll all have heard of the stories of, well, with some black holes, you get what they call spaghettification, where your feet are closer to the black hole than your head, and so your feet feel a stronger pull than your head does. So you gradually get elongated by the difference in the gravity and basically turned into a string of spaghetti. Messy spaghetti, but nonetheless the similar sort of shape. And that would be true with our galaxy, with Sag star. But with M87, it's not, because you're so far away from the black hole when you cross the event horizon that your feet don't really feel a significantly different gravitational effect than your head. And it's the same for the magnetic field. The magnetic field doesn't know it's crossed the black hole event horizon. It's just minding its own business and carrying on doing what magnetic fields do. So one of the ongoing programs that I'm involved in is to disprove the no hair theorem. And we're almost there, because you can see what's happening with the magnetic field. And with data that's already been taken, actually, but hasn't had time to be reduced, your shipping containers full of data is perfectly true that you said earlier, Andrew. People literally ship the data around the world on physical sort of hard, well, solid state devices, because if you tried to pump it over the internet, you'd kill the internet. The data would be more than the data rate of the entire internet put together. It's phenomenal. But so that's my excuse for why we haven't published this yet. But we are working, and it has worked reasonably well, on the subsequent data. And I said we were operating at about a millimeter. It's actually about 1.4 millimeters, 230 gigahertz thereabouts. We've actually managed to take pictures at 345 gigahertz, so about 0.8 millimeters. And 1.4 to 0.8 is getting close to another factor of 2 in resolution. So when we manage to analyze those images, and there are people working on it, and there's definitely detections there, then that's another factor of 2 in resolution. We'll be able to chase the magnetic field even closer down onto the event horizon. And if it doesn't change between the two, then there's no reason to suppose it will change after that. It'll just keep going. As I say, the magnetic field does not know it's crossed the event horizon. And at that point, we will have disproved the no hair theorem, which is something that's been around for goodness knows how long. You know, the old one, a black hole only has two properties, sorry, three properties: mass, charge, and spin. To that, we will be able to add magnetic energy density.
Thank you, Derek. There are two questions in the chat, and then I'm going to call time, gentlemen, please.
Fine by me.
Right. I'll take one. Will these supermassive black holes have dark matter halos, if dark matter exists? And will the EHT show the existence of these halos?
Oh, wow. No, that's an excellent question. First of all, dark matter exists. You know, It just is. It would be arrogant of us to think otherwise, that we've actually explained the entire universe. Clearly, I'm perfectly happy to say, yeah, 96% of the matter in the universe exists in forms we don't know about and don't understand. As I say, it would be arrogant to think otherwise. But the dark matter halos tend to be on a much, much larger scale, and they surround the entire galaxy. But they have a spherical distribution, which is how we know they're there, because the rotation curve of a galaxy, those of you with 21 centimeter receivers on your radio telescope will be able to measure the rotation curve of the Milky Way and verify the so-called flat rotation curves, which tells us that the mass in our galaxy is spherically distributed. And even though what we can see is just distributed in a disk. And for a spherical distribution where there's more mass in the center than at the edges, then clearly there must be dark matter around the black hole. Trying to tie that one down is going to be really, really challenging. But there are indirect ways we could look at it. So, for instance, we know there is a relation between the mass of a galaxy as a whole and the mass of the supermassive black hole that it harbors in the middle of it. So there is quite a strong correlation there. If you've got a more massive galaxy, you've got a more massive black hole in the middle of it. And that's difficult to explain without saying that it's the dark matter halo that is determining both. And so I can give you an indirect answer that yes, it looks as if it must be playing a role, but in terms of proving it, either by observing it or by looking at what it's doing, no, I can't tell you definitively, but my gut feeling is yes.
Okay. And the last question for the evening. It's been theorized that very active black holes kill galaxy star formation by blowing the hydrogen gas needed out of the galaxy. Our galaxy has a small black hole at its center. Is that why we still have active star formation?
Yes, that's a very good question. That's correct. But what we think has happened is that the black hole has, or the jet that used to come from our Sagittarius star black hole has actually created the cavity at the center of the galaxy. It's blown that material away. So once you get inside the central region of the galaxy, there is no star formation happening right in the center. We have what's called the central molecular zone, which surrounds that, where star formation is happening, but go any closer in than that, and there's nothing. And that is what's happened. We think that our black hole has killed star formation in the very center of the galaxy. Fortunately, it hasn't killed star formation in the rest of the galaxy, because the other thing I study is star formation in our galaxy, and I'd have nothing to study if it wasn't there.
Okay, Derek, thank you very much for a very interesting talk. We've had two very interesting talks tonight, which I have thoroughly enjoyed, and I trust you all have as well. It is definitely on Paul and I's books to invite our two speakers back at some point Derek, when you have some new results, we would be delighted to hear from you.
I'd love to
And
come back. Yeah.
Michael, when your weather is better, I think sometime when it's sunnier, we'd be delighted to come back and hear more of your tales of building an observatory in Portugal.
Yeah.
So
Okay. Cool.
without
Okay.
any ado, I'll say thank you very much, everybody. Good night, and see you for the next presentation at the end of the month.
Thank you, everybody.
Yeah, thank you.